welcome. Happy almost spring, everybody. My name is Sydney. I will be the moderator for our awesome mycoremediation panel that we have together for you today. Just wanted to let you all know that this event, in addition to being here at the Missoula Public Library, is being put on by the Western Montana Mycological Association. We are a 501c3, been around since 1991, almost before I was born. And one of the things that we are all about, in addition to this particular event, is providing people with great educational opportunities surrounding mycoremediation, fungi, mushrooms in the Western Montana area, also focusing on helping people get out and appreciate mushroom culture and protect areas that are mushroom foraged in general. So we're glad that you're here. Thank you. I'm going to do some intros of our panelists here, and then we'll be doing there's going to be a couple presentations. What is mycoremediation, kind of a general overview. Mark Vander also has a few slides he wants to share, and then we're going to launch into the Q&A. I'm going to have a few questions. After that, you all are welcome to raise your hand. I'll come around with the mic, and you can ask away. And the idea is this is going to be a educational, illustrative event. We're really excited to kind of take this stuff out from under the ground, so to speak, and bring it into the public awareness and consciousness. So thank you for being a part of that. Who's here? Up in the front of the room. Right next to me, we have Cliff Bradley. He is the founder and president of Montana BioAgriculture, Inc. In his 30-year career, he has worked with fungi for applications in agriculture, forestry, and bioremediation. He works with fungi, including all stages from strain isolation to commercial scale production, and in his previous company conducted mycoremediation of petroleum, chlorinated compounds, and explosives. Boom, baby. All right. Egan Jankowski-Bradley. They kind of look related, don't they? Egan manages Montana BioAgriculture laboratory operations. He has over 10 years of working in fungal laboratories, including strain isolations, fungal production, and field trials. He recently conducted a pilot demonstration of mycoremediation of acid mine drainage in the Pioneer Mountains of Montana. Egan has also been an active member of the WMA for decades and is passionate about mushrooms. Mark Vander, on the very end there, is the founder of Bad Goat Forest Products. He's a forester and restoration ecologist. As a professional forester and soil ecologist for more than 20 years, Mark has been practicing and mentoring long-term sustainable forage management in Montana and is well qualified to review forest plans and assess project sites. And the man with the braids in the middle there is Larry Evans, who's one of our board members of the WMA. He's been one of the mycologists at large for over 40 years, cruising around both on a commercial and a recreational basis, foraging for mushrooms in the wild. If anyone could teach you about mushrooms and mushroom hunting in Montana, it's probably Larry. You can find him in the mountains, if you can actually find him. He's probably in the mountains, but he's a very prolific mushroom hunter, teacher, cultivator, songwriter, and cook. He's organized heaps of forays, festivals, and workshops around mushrooms in the Rockies, Pacific Northwest, Bolivia, and Jamaica. He's one of the founders of the Western Montana Mycological Association, wrote a field guide to mushrooms of the Amazon, and has appeared in Ron Mann's documentary, Know Your Mushrooms. So just a little warm welcome to all these great people we have up here. Just to offer too that these are some of the best mentors that we have in our community around mushrooms and mushrooming, and in many cases they have decades and decades worth of experience. So it's a real treat to get to have this many years with us in a room, just to honor them for their time. Cliff, if you would be willing to take this mic from me.
Well, I don't know whether I should sit down or stand up. These are.
Whatever's comfortable for you.
I think standing up is probably easier. I get to walk around that way and do crazy stuff. Yeah, so this is, there we go. Mycoremediation, we're going to talk about organic pollutants and heavy metals. So we go to the next one. When you go to people in the remediation industry, if you will, there's bioremediation. Covers a whole range of things, from natural microbial population, just hoping what's there will eat what you've got a problem with. Biostimulation typically is adding bacterial cultures or adding nutrients to sort of make whatever's living in the soil or water stimulated to break down your waste a bit better. Bioaugmentation is typically adding bacterial systems to some kind of waste treatment. And then fungal bioremediation, which is what we're going to talk about, is introduced fungal cultures. It's sort of fungal bioremediation. We're going to talk about two things here. One, organic pollutants. Fungi will degrade organic molecules. They don't do much to any other. They'll absorb things, but they need to eat some carbon in the process here. And we're going to talk about some petroleum and polyaromatic hydrocarbons and chlorinated compounds. This is where the fungi are really good. Egan's going to talk about metal sorption here in a bit. And one of the things I want to talk about some is just, we don't often appreciate the scale of the mess that we've left behind here in the petroleum age. This is a little outdated, a series of incidents of petroleum spills in various parts of the world. And one of the things everybody here may have heard of Exxon Valdez in Alaska, that's actually number 48 in size. I mean, it's rounding error compared to the messes in Nigeria and Ecuador and places. And I want to talk about this a little bit for two reasons. One, just to appreciate the scale of the mess. And number two is the scale of this is the only way it's ever going to get remediated is with biology. You're not going to dig up the Niger Delta and haul it away and bury it somewhere else. So that's why we're talking about biology. And the scale ranges everywhere from the Niger Delta, where the oil companies have spilled something in the order of 550 million gallons of crude oil on the Niger Delta. Ecuador and the Amazon basin, Larry and I took a trip down and actually got to see a bunch of this. Somewhere in the neighborhood of 50 million gallons of petroleum and more than 1,000 unlined pits that Texaco, and then after Chevron bought Texaco, that is left behind and walked away. And these are just holes in the ground full of petroleum, unlined. This was stuff that they were doing in the 1990s in Ecuador that was illegal in the United States in 1950s. Then, of course, you remember the blowout in the Gulf of Mexico. That was like 200 million gallons of petroleum estimated. So to give you an idea of the scale, this is the gas flares of the Niger Delta. From the left there, about Lagos down to Douala in Cameroon, that distance is over 400 miles. So they give you, that's like lighting up the night sky from here to North Dakota. And this is an inventory of a couple years ago of the oil spills in the Niger Delta. Go ahead. And this is some of just what it looks like. I mean, it is just a complete, unbelievable mess. Okay. And it's not unique to Africa or South America. This is the gas flares in the Bakken oil fields in North Dakota. It's never made sense to me that we are fracking Pennsylvania for natural gas and we just burn it off in North Dakota. But that's the system we have, I guess. And again, in the United States, even in our own Missoula here, or in Montana, Stone Container out here has several 100,000 cubic yards of petroleum-contaminated soil underneath it because they ran that whole plant on bunker fuel for decades, and spilled a lot of it. So there's no shortage of places to clean up in Montana. And this is one, I don't know if you can see the mushroom there. This is a little biology because life is adapting to this mess. These are fungi that we found in oil pits in Ecuador. The next slide. You can see that one growing out of the top of the log. These are logs that we pulled out of the pits that are just saturated with oil. So life will adapt to these. Go ahead. The issue with mycoremediation of petroleum or hydrocarbons is there's just, there's 200 different compounds, give or take, in the average crude oil. And given enough time, sort of other methods of bioremediation might take care of it. Bacteria will eventually degrade parts of it. But the really nasty stuff, the heavy hydrocarbons, the aromatic compounds, really resist natural degradation. And these are the ones that are toxic. I don't know if you've ever heard of some of these terms. There's benzopyrene is very carcinogenic, absorbed through your skin. And these compounds are the ones that are not degraded by natural bacteria and petroleum. And they just, there's still, you can still go to Alaska and find oil on the beaches from Exxon Valdez. The other big issue here in a lot of bioremediation are chlorinated compounds, because in nature doesn't attach chlorine to carbon. That's just something that very rarely happens. We do that all the time, making pentachlorophenol for wood preservatives, dioxins, PCBs. And this is another place that's pretty close to home in Montana. Underneath the pole treatment yard in Butte, and under the freeway there, as you go into Butte on the west side, southwest side of town, there's about 220,000 cubic yards of dioxin-contaminated soil underneath all that. And they have no idea what to do with it except put a fence around it and hope for the best, literally. Yeah. And this is where the fungus comes in, a particular kind of fungus that we work with for remediation, white rot fungi. And you'll see these out in the forest. If you find a rotten log, some of them are brown. Those are brown rot fungi. But white rots eat the lignin out of wood and leave the cellulose, which is white. The lignin is brown and the cellulose is white. Lignin is what holds wood together. And lignin is a very complicated molecule. Very this big structure like you can see on the left-hand side of this that are a bunch of in biochemistry terms, aromatic rings. And what happens is the white rot fungi have evolved a really unique enzyme system. No other form of life on the planet has these. And they're enzymes that are very nonspecific. Most enzymes you think about if you learn in biology class are very specific. There's a lock and key kind of concept that only one reaction will happen with one enzyme. Well, the enzymes that were produced by these white rot fungi, peroxidases, are very non-selective and will degrade all kinds of organic molecules, next, including the ones that are really nasty from oil. Yeah, and you can see the similar structure and they will also degrade chlorinated compounds. And I can, if somebody wants to have a biology lesson or a biochemistry lesson, I can tell you how all this works. But basically, these enzyme systems are able to degrade all kinds of different toxic wastes, these kind of ring compounds that resist other forms of degradation. And the way we do mycoremediation is actually pretty straightforward. You can do this, one real big advantage is you can do this on site. You don't need to haul the soil somewhere else. And if you're doing a very large-scale site, you can set up producing your white rot fungus on site or produce it to some central location and transport it to smaller-scale problems. What we do and what we've done over the years is we grow fungi like Pleurotus. Oyster mushrooms are actually very effective as bioremediation white rot fungi. Grow them on straw, wood chips, or something cheap and readily available. And then once you get the culture to the right point, there's some tricks to it, but once you get the culture to the right point, you've got a whole bunch of fungus growing on the straw or whatever. You just till that mix that with the contaminated soil. And sometimes if the soil is contaminated really deep, you have to dig it up and spread it out and mix the fungus with the soil. And hopefully, I mean, this works better in warm weather than cold weather, obviously, and there's a bunch of limitations to it. But basically, if you mix the fungus in the soil, the enzymes will degrade the organic compounds, and then then once those compounds are opened or degraded partially, other microbes, including the white rot fungus, will eat them. And the end products here are carbon dioxide and water if you get it right. I mean, that's the advantage, is when you dig up something and haul it away and put it somewhere else, it's still there. It's just better contained, perhaps. In Ecuador, they were talking about digging up all of the oil pits and hauling it somewhere else. It was like 200,000 truckloads of this stuff to put it on some other place. Well, it's still going to be on some other place, so just getting rid of it on site seems a lot better to us. And actually, in U.S. economics, it's a lot cheaper. It's getting very expensive to dig up soil and haul it to Utah and put it in a toxic landfill, where you can treat it on site for much less and get it done. So I think, yeah, okay, Egan's going to tell us all about acid mine drainage.
All right, the other part we were talking about that we see the biggest potential in mycoremediation and the work we do is with on heavy metals. And so in Montana, it's a big problem. There's all these acid mine drainage, which is when you open a dew mining and you open up the earth and expose it to oxygen and water, a sulfur ore body is going to contain sulfur-eating bacteria that then create sulfuric acid and drop the pH and liberates all the metals. So that then you get what they call acid mine drainage, which is lower pH, it's acidic, and then there's these liberated metals in it that are toxic to aquatic ecosystems, ranging from the insects to the fish to the birds, so on a large level. And on a large scale, there's open pit mines like the Berkeley Pit in Butte, which is kind of a very large toxic waste site, miles wide by mile deep. And then there on the small scale, there's thousands of old mine sites across the West. And in Montana, there's thousands in our stretch of the Rocky Mountains. And there's two main fungal systems that deal with this. There's a bioabsorption, which is a biological ion exchange, and that's a system that we've worked with more, and then yeast sequestration, that's actually a yeast that was discovered in the Berkeley Pit, being able to gather the heavy metals and sequester them away. And there's been a ton of academic research over the years. People have been discovered that the bioabsorption of heavy metals since the 70s and 80s, and but they started with other things, from seaweed to wood waste to activated carbon. There's a lot of kind of natural things that will absorb metals. But they were found, fungi to be most efficient. There's the mechanisms. It can absorb a lot of different ranges of metals, different conditions, pH. All these systems, every mine waste mess is different, has different metal concentrations, different pH, different other issues and concentrations, and fungi can deal with that. Okay, good. We've done lab assays as well as from the literature, and there's a host of different fungi that can absorb metals better than other. And one of the best species, and even Larry brought little baggies of this, is Rhizopus. It's consistently the most effective. And Rhizopus, most people might know, is what they make tempeh out of. So that soybean product where they put mostly whole soybeans into a little brick, and it was originally wrapped them in banana leaves, and that was where the naturally occurring Rhizopus. And then in industrial uses, they make different organic acids. Lactic acid is a big one, or citric acid to make your sour candies or things like that. And there are also a bunch of domestic isolates. So people produce tempeh here out of U.S. isolates, not just requiring the ones from Japan. Okay. And so the same thing, the bioabsorption is the same as a fungal biologic ionic exchange. And so the way that you can think about this is the unique cell wall structure. Rhizopus has a bunch of carboxyl units, so there's, once again, we can get into weird chemistry, but there's a double bonded O that's searching for a positive hydrogen, a double bonded oxygen, and or anything else positive, which all metals have a positively charged to them. And the cells don't need to be alive once they're utilized, so you can grow them in mass, and then once the cells are grown, then they still will attract the metals to it, so it has big advantages. You don't have to constantly growing it and feeding it and do all this. It's got a high capacity for different metal ions, either single ion or mixed metal matrices, and so the chemistry can get complex once you're dealing with all these different metals mixed into a system. But fungi can absorb 25 to 30% of cell dry weight in metal ions, which is a lot. A fungus can grow very fast and very efficiently, and so when you get 30% absorption of the metals, then you can absorb a lot out of the environment. One of these good examples on the Montana landscape is our small company was working with the Big Hole Watershed Committee and Beaverhead County and working on the Elkhorn Mine, Adit, and Mill, which is in the Southern Pioneers. So you can see this is the old mill building. It was, I think, originally a 4-story structure, and then now it's just rotting away. And then the adit, which is where they got the metals out of the ground, the big hole in the ground, now there's a stream just flowing out of the mountain that is full of heavy metals. And there's some life and algae, kind of like Yellowstone, growing in it and making it orange. But otherwise, it's got a low pH and is full of a range of heavy metals from silver and copper and arsenic, just flowing readily into the environment. And so we did a pilot study this last summer with the Big Hole Watershed Committee. And so I designed from the lab, this is then brought up to a pilot scale, that this is the rhizopus culture growing in large pipes that are 6 feet tall and 6 inches around. But the rhizopus is just corn cobs, because you need something to hold the cells. If you got all these fungal cells and you get them wet, they would have a tendency to kind of collapse. And so it allows it to kind of be in a fixed bead column so you can run fluid through it. And the way we did it was we ran a pump into the stream and then bottom fed the liquid up through the bottom of the pipe and through the top in a series of columns, and then we had clean water come out the 4th column. And then with this small little pilot system, which on scale would probably be about 120 pounds of dry weight rhizopus cultures, we cleaned up well over 600 gallons of acid mine drainage from this one site on our first attempts this summer. So this is just a small grant, just proving the practicality of acid mine bioabsorption of metals using fungus. So yeah, the statistics on this one pilot study of those 4 pipes, and we had a little over 100 pounds of fungal culture, we cleaned up over 500 gallons of the water. And this is a little unrefined. This was our first sort of practical attempt on the landscape. We went up there 3 times to the mine site. And so we're continuing research. Hopefully we'll have continuing grant money to do so. We will be able to clean up more and as time goes on. And, oh, Cliff had that last one. And one reason why we find, one more back, Cliff, left, that these fungal bioabsorption columns would be practical on a large scale is they're low cost, utilizing corn cob fractions, the woody bit from inside corn. And then just to feed the fungus, we use a little bit of barley flour, and then feed it some water and oxygen, and then a little bit of rhizopus biomass to grow and fill the whole thing. And then if this is something to go up on scale, what would you do on a problem, especially somewhere like the Elkhorn Adit, where you're continually making acid mine drainage, it's a stream, as you would figure out a larger system of either columns or like ideally something that's probably lagoon system, but corn cobs and rhizopus, you can low heat ash, so you can incinerate it and left with a very small amount of a mess. It's not like, that's one thing that we always want to get away from in bioremediation, is not creating a separate large-scale mess, moving it around, doing other sort of things. And so if you had a low heat ash incinerator, you're left with a little bit of carbon and metals. And depending on the mine site, you might even be able to harvest the metals, reclaim the metals from that system. And then the other, next Cliff. The other yeast that we were talking about was isolated by the Sturley lab in the University of Montana, and they originally isolated it from the Berkeley pit, and it sequesters the metal ions inside their cells. And they haven't been able to do much with that technology besides knowing about the yeast, but we've been in talks with them, and they allow us to do more preliminary research on that yeast. So they'll give us the culture and see if we can grow it and make it a larger treatment system. Okay. And then we wanted to talk about some of the issues and barriers with getting mycoremediation on the landscape. And it's regulations and institutional inertia. I mean, like I was saying, and Cliff has been saying, people have known these biological systems work since the 60s and 80s, and everybody's done lab scale benchtop research where, hey, look, it works really well in a flask. How do you make it bigger? And then each site is different. From oil spills to containment and different specificities. And the one part where we're working at it and actually good at what we do is the production of a large-scale fungal culture. And so we can grow fungus on actual physical tons. And what we need to do is, these are industrial-sized messes. We need to take it from the lab and actually clean it up on an industrial scale. We need the money and the know-how to do it. No one wants to pay to clean up the toxic waste after they make it. And then so we just need to work on more treatment and delivery systems. Okay, unless you have anything to add. And here, Cliff can talk about this.
Okay. Well, Sydney asked us to talk about what some of the cutting edge research or what cutting edge needs in bioremediation. And as Egan said, there's been decades of lab research in this kind of field. And what we see is the real need for research is just how to get out of the lab and into the field. You're going to have to move from people, growing cultures in a flask to literally thousands of tons of fungus culture. And we know how to do that. Other people know how to do that, but it's going to have to be that sort of scale to deal with this. We need practical treatment systems, particularly for water systems. We got to find good ways to treat large volumes of water. One of the issues at the Elkhorn site is there's literally a small creek flowing out of the mine, and it's trying to figure out how to deal with that volume. And it's not tomorrow afternoon or you're going to clean it up in the next 3 weeks. That's flowing out of that hole in the ground for geological time. And we got to deal with issues like that. These have to be scalable at a cost that can be afforded. And again, the fungus growing on cheap substrates is a way to do this. In some cases, you can recover metals out of some of these wastes. That has some value. The largest ore body in the state of Montana is the water in the Berkeley pit. If you take the volume of water times the copper concentration, it really is literally the largest source of copper in Montana, probably one of the largest in the world. But it's just parts per million, but it's a lot of millions. And then how to convince the regulators that this works. That's one of the big issues in inertia, that you have to be a best available technology to be used under EPA regulated sites or even Montana Department of Environmental Quality sites. But to get certified as that, you've got to demonstrate it. And to demonstrate it, you've got to go to real sites. And so there's a whole catch-22 that we've been dealing with for years with the regulatory system and how these sites are dealt with.
They like to say you pass proven technology, but how do you prove technology if they won't let you?
So.
Well, what is the benchmark for provable?
Yeah.
What is enough? What is provable? What is provable enough? Yeah, that's kind of a moving goalpost that we've been chasing for decades now.
But one of the things that's driving a lot more looking at bioremediation, and we have actually a proposal pending with the U.S. Department of Transportation now to look at cleaning up oil spills from pipeline ruptures, which there's a lot of in the U.S., and that they're finally starting to look at this. And one of it is just the cost of digging up and hauling things away. And EPA now has rules that if you a hazardous landfill, you have to monitor it for 30 years. And so that is starting to add a lot of cost to hauling and storing toxic waste forever. So these things are coming, but it's been slow. I did my first real scale mycoremediation project in 1996, and here we are. So, and that was actually 10,000 cubic yards of contaminated petroleum contaminated soil in Washington State that we cleaned up. But they changed the rules, and at the time they would have had to incinerate that, which is very expensive, and then they allowed the rules changed. They let them bury it in landfills. And at the time, landfills were cheaper than fungus, but fungus were cheaper than incineration. And so the market changed a lot on us. And so here we are again.
Thank you both. Yeah, exactly. Thank you. This is partly why we were so excited to have Cliff and Egan here talking with you all, because the work they've been doing in their lab behind the scenes is so amazing. And anything that comes from you all hearing about this, whether it's you work with the State Department or you know someone who works in the State Department, I can only hope that serendipities come from a meeting of minds like this that will allow us to push through barriers that have existed for you all historically. But thank you again. Mark has a few slides that he wants to share. Mark, I can click away for you over here if you just indicate when you want me to move forward.
All right. Is this working?
Yep.
It is. Great. All right.
I tried turning it on. Okay, great.
But I still don't think it's working. I don't know.
Try the other one.
How about now? How about that? Yeah. Yeah. So that was crazy.
Never happened before.
My talk is nothing like that one. I don't know anything about fungi or mushrooms, and I was asked to come. Yeah, I was asked to come here because I know something about soil biophysics, and soil biophysics is a word I made up. So if you never hear it again, that's why. And it
sounds really good.
It does.
It's really highfalutin.
Yeah, and I studied soil biophysics forever, and it's basically how biology influences soil structure. And the subtitle to this, several subtitles because I couldn't figure out which one I wanted to use, how to create, promote, and maintain water-stable aggregates. And that's the big take-home message here is water-stable aggregates. What are they? How do you make them? And the third thing I said there was coarse woody debris. What is it good for? Well, we'll talk about that. Go ahead. We're going to have to do a little tiny bit of a soils primer here. Soils is made out of sand, silt, and clay. That's what soil texture is. It's the relative amount of those three things. Sand is huge, silt is not huge, and clay is really, really small. And clay, sand is broken down rock, silt is broken down rock, but clay is something vastly different. It's a crystal from a soil that has dissolved and come out of solution as a crystal. So it's very different stuff. And texture, we know what that is now. Structure is how a soil is aggregated, how those three particles stick together. Pore space is the space between and inside of those aggregates. Gas exchange is hugely important. You've got to have gas exchange in soils or it dies. And keep in mind, soil is a living thing, or the soil we're talking about is. And then, of course, water holding capacity is a big deal. Go ahead. Your average soil is about 50% pore space and 50% solids. And that's an average nice soil. Go ahead. Okay, water-stable aggregates. Here they are. The thing on the that black blob on the right, those are awesome water-stable aggregates. These are both samples that were saturated in a little dish drainer, then plopped upside down. That blob on the left lacks aggregation, and when you put it in water, it just puddings out. And you can see the dirty water coming out of there is one sign that you've got awful water-stable aggregates. The clean water on the right-hand side is a good sign. That's a good bunch of water-stable aggregates. This is a super easy test. You can do this at home. I got these little screen things that you catch garbage in your sink. You get them at the dollar store. That's what I use for these. Okay, this is what this is a cartoon of an aggregate. And remember, aggregates are created and maintained by soil biologic activity. That's the big deal. So you got to have life if you want these aggregates. Go ahead. There's a good-looking piece of forest soil, just the litter, duff, and mineral horizon. This is what your average soil looks like in the forests of Montana. Go ahead. I work mostly in forest soils, and this soils you're looking at right here, they look, the forest looks kind of nice. This is a what's called a TSI, a timber stand improvement cut. And they cut half the trees down for pre-commercial thinning for future wood. But they did a good job here of leaving the debris there. That's not normal. Most of the time these days, the fire folks would have a fit and make you pick up every stick. But the woody debris in most of our forests right now is lacking. Your average tonnage per acre of coarse woody debris should be between 10 and 15 tons per acre. These days, we're finding around 2 to 3 tons per acre. So there's a lot of carbon out there missing. Yeah, go ahead. And this is where the carbon's going. It's going into these giant slash piles to be burned, and not an awesome use of this stuff. And you can look around there. This used to be a mature forest just months before this, and these are called overstory removal cuts. If you think this isn't happening, this is on national forest land. So this was a mature stand of trees. The goal was to take out the big trees and leave the small trees for the mill. And 80% of that soil there has been compacted in those units. It's still green, but it's compacted, and the aggregation there is not awesome. Here is a landing. This is what happens when you burn one of those piles. This one got lucky, this landing. This has carbon source on it. We are doing remediation in the forest now using fungi by loading carbon on the soil surface. And by carbon, I just mean forest slash. So we're decompacting roads and basically increasing soil biologic activity. Now, the cool thing about fungi is it is a hunter. It looks for stuff. And if it senses somehow that there's a carbon source up there, in the air, it'll go up and get it. So we lay this slash down. The fungi breaks through the compacted soil, grabs the carbon, and brings it to depth, adding water-stable aggregates the whole way. We've, through our research, have found that we can recreate water-stable aggregates in 2 growing seasons, which is pretty awesome. And we didn't think that was possible, but we had to really load it down with fresh green slash, but it did work. And now these techniques are fairly common in the Forest Service, where they're laying down slash on old landings and roads, and it's all for soil remediation purposes. Go ahead. This is another lost opportunity. We have a compacted roadway, and then we have a pile of slash. And again, the agencies will not allow that slash to be put out there on the ground for fear of fire hazard, even though it's not really a fire hazard when it's linear like that. But it's a bummer to lose it. Here's the water-stable aggregates. A lack of water-stable aggregates will do all these awful things. Water-stable aggregates run the world right now. It will decrease water infiltration, increase overland flow, increase floodwater volume and energy, increase erosion, increase sediment delivery in size streams, choke channels with sediment, reduce late-season spring flows, compromise soil aeration, decrease plant vigor, and basically lead to desertification. And we've seen this over and over and over again, not in our country because we're a little behind, but in other places.
California.
Yeah. And to relieve compaction, there's 3 ways to relieve compaction, which is just that breakdown in pore space. Mechanical, freeze, dry, and wet and thaw events, and then increase soil bioactivity. And I got to tell you, the bioactivity works. We've learned that if you throw slash down on a road, a normal road without slash will stay compacted about 80 years. With slash on it, about 25. So it takes some time, but it's helping a lot. Yeah, go ahead. Oh, yeah. So this is a desertified place right here. But it only acts desertified. It is not a desert. This is just north of Beirut. And they get 28 inches of rain there. But it acts just like a desert. It's awful. And as a comparison, Missoula gets about 16 inches. So we're starting to see our watersheds desertify in kind of a big scale because of these lack of a carbon source on the surface and the damage to these water-stable aggregates. And if you want to see some of these aggregates, go home and look in your garden. That's where people really see them. That's where they're at here in town. That's all I got.
Thank you very much, Mark. I'm just going to...
Oyster mushroom thing is right
Oh,
down in
okay.
the Firefox.
Perfect. All right.
Here we go.
Larry, do you want to take that other mic? While you
Sure,
talk
I
about?
just-
No, you take... Yeah, there you go.
Whichever one is.
And
Hello? Not that one. Hello?
it takes a little while to kick in. Yeah.
Okay, there we go. Can we just make it full screen? Yeah, this is just a short video that we put together to explain our oyster mushroom eating particle board project. The particle board project started 4 years ago now. We had a project at Home Resources for over 2 years where we collected particle board from people who brought it in. Home Resource wasn't able to reuse particle board, and so as a result, a lot of it was going to the landfill. It's a problem in the landfill because the resin that holds the wood chips and the particle board together is urea formaldehyde. It's made by putting urea and formaldehyde together. Guess what? And then it forms this solid rosin. That can be very toxic if it goes into your watershed because it forms formalin, which is a carcinogen. And so seeing this problem with solid waste of the particle board, we were inspired to take the waste oyster mushrooms and hericium, or lion's mane, from mother fungus out at the Y, and those are his byproduct blocks that you'll see there, yeah. And then we use those, stack the particle board, we wet the particle board, we stack it, we put the bricks in between, kind of break it up, and you'll see it completely degrades over a period of a season or two, and this has been very, we haven't tried to concentrate the reaction at all. It's just pretty much a natural process. We've been kind of containing it here and having the mushroom eat this urea formaldehyde so that it doesn't go into the water source. The urea formaldehyde is a really good food source for the mushroom because mushrooms need nitrogen, and urea, of course, has got a lot of nitrogen in it. Mushrooms need about 700 times as much nitrogen as plants. They need nitrogen to make chitin, which is in their cell walls. So it's a very important nutrient, more important for fungi than it is even for plants, okay? So here's just a 3-minute something video that kind of describes our project. Mike Sanders here is our current lead for this project, and so he's happy to answer questions or tell you about upcoming activities. All right, thanks.
Everything has a fungus that eats it when it's gone, sucking out those nutrients so life can carry on. Every tree has a fungus that inhabits its roots, spores that travel with the seeds and catch the sprouting shoots. Hey, everyone has a fungus, and everyone should know what the fungus is doing to your barley or your toes. Hey, whether or not you eat your fungus once or twice a day, someday that fungus is gonna eat you, 'cause that is nature's way.
This is now down at the Garden City Compost Facility, and you can see it down there.
Everyone has a fungus. If you know
overall volume of the particle board decreases by about 1/3 to 2/3 over the period of a year and a half.
Sucking out the nutrients so life can carry on. Hey, whether or not you eat your fungus once or twice a day, someday that fungus is gonna eat you, 'cause that is nature's way. That's nature's way, baby.
Product that we're getting out of this here, you know, and it right there, it's pretty solidly, you know, it's decomposed all the way through. So, that's all. That's what
Yeah, I took a video of all the action because we were right at the intersection, but then I didn't record anything. Which way did you guys go?
There you see the blocks again on the side where we're adding extra mushroom spawn to the load of particle board there. It's kind of hard to make an exciting video about this.
And yeah, there's this bunch here, and this is about how it looked when it first started, because I was there at the beginning.
looks like a pretty nice spot.
Thank you, Larry.
Now we can put a vehicle here.
Thank you, Larry. Also, for those of you who didn't catch that, Larry was the soundtrack in that.
And this is one, before we start taking questions, I'd like to announce too that we're starting, maybe you saw our posters over here, that we're doing the Robbie Flynn fungal product contest. Yeah, and you can see that it's going to last for a year, and we will offer people fungal cultures and substrate if they support for any projects that they want to do. We encourage science classes and teachers to get involved, and our goal is to design any new creative type of project, whether it's a filter or a doorstop, using fungi as the main ingredient. So we'll talk about that more after a bit, but yeah, let's keep on with our discussion here.
Sweet. Oh, man. That was really cool. Thank you all for showcasing that amazing video. I agree, Larry. I was there. It is hard to make an exciting video about particle board breaking down. It just takes time, you know? Like, it's like watching particle board break down. Exactly. I was going to throw out a few questions for all of you to answer as you see fit. And then I'm going to hand it over to you all in case you have any questions that you would like to have answered. One of the questions we get a lot, and I know this sounds super silly, but you know, in a mycoremediation context, can you eat the mushrooms? Is that mic still on? Yeah. Can you eat it? We get a lot of that in general, but.
Well, the way we do mycoremediation, we don't get mushrooms. We're just working with the mycelia, just the mass of cells, where we actually don't want mushrooms because they stop producing the right enzymes or they don't absorb the metals out of the water. So we don't worry about mushrooms at all. We actually need to harvest our cultures before they ever make a mushroom. Sometimes they've gone too far and then we have supper, but as far as that's a fundamental difference here. Mushrooms are the fruiting body, and it's the mycelia that we're working with that are the actually active growing enzyme producing part of the fungus.
There are a number of species of mushrooms that bioaccumulate heavy metals, and I'm sure Egan can go into this at more detail, but species like the giant puffball, the common champignon, the button mushroom, and shaggy mane are all mushrooms that tend to accumulate heavy metals and concentrate them in the fruiting bodies. So if you're picking puffballs out by the mine tailings, you might have another thought. Yeah, that kind of stuff.
It's a good distinction to make, Larry. Do you want to add anything to that?
I'll just add one thing in relation with Mark Vander and building soil, is we've actually tried to get the USDA on board with building soil on the forest and to take those slash piles and instead to create a secondary market and break down the slash piles with conifer-loving mushrooms. And then it's a secondary income opportunity for someone to go back and harvest the mushrooms, and then you create a big carbon sink in the soil, and it's compost. It will hold on to moisture, it will not burn, it'll be a big, nice compost pile with mushrooms growing out of it at the end. And our response from the USDA was, fungi don't break down trees. And our grant was denied. So we do find institutional knowledge to be a little hard at times to overcome that, and so our grant was fundamentally just denied, even though everybody in this room knows that fungi break down wood. So.
See, this is why we need all of you, okay? We can't do this by ourselves. It takes a whole village to change the attitudes of the system. Obviously, this whole presentation you've been giving, you're talking about how mycoremediation works. I think that everybody in this room believes you when you say that it works. But how clean is the water? How clean is the soil? Like, could you grow a garden or could you drink the water that comes through some of these filters?
Yeah, where we've had success, and one of the notes I want to make is we need to work more with people like Mark, and Mark needs to work with us, because the soil structure has a lot to do with whether bioremediation will actually work, mycoremediation will work. You get a really heavily compacted clay, it's a lot harder to deal with than a nice sandy loam, for example. But when we've had successful projects, yeah, you could grow. The project we did in Washington, we reduced hydrocarbons, heavy hydrocarbons, to an old railroad maintenance yard that they just dumped the oil for decades into a pit, and we cleaned that up. It was, usually you hear about contamination in parts per million. Well, this was percent. I mean, there was like 5% crude oil. I mean, just heavy hydrocarbons in some of this stuff. And when we were done, it was non-detect. I mean, you couldn't find oil in there. You could actually grow something on it.
Yeah, and with the biofiltration system afterwards, I mean, I'm not usually go around drinking stream water, but overall it would be like drinkable. You wouldn't have the heavy metals in there afterwards. So, I mean, that's the end goal of actually cleaning up the system and of mycoremediation, is like that we've been talking, is cleaning up on site, in situ, not moving it, not creating multiple messes, and doing it using biology. I mean, Mother Nature has figured out how to do this for millennium, and it's our problem as humans came and created industrial crazy-sized messes, and we haven't created industrial-sized cleanup operations besides heavy machinery.
Anything else to add to that, Mark?
Thank you. I know that you did cover this a little bit, and I also know that it depends on the species of mushroom and what kind of toxic compound or heavy metal we're talking about, but just to make sure everyone's really on the same page, because I don't know everyone's scientific background, what's actually happening to the heavy metals? Like, in some cases you talked about how they're being isolated and sequestered. In some cases you talked about how they're being bonded with another compound or another molecule such that they are neutralized and they're no longer as volatile. Maybe you could speak to that a little more.
Yeah, with the heavy metals, and like Larry was talking, there's even mycelium and normal attenuated mushrooms that you will find can absorb things. Like driving along, you can find the shaggy manes popping up out of roads. I mean, it's crazy. This little fragile mushroom will pop out of the road and eat other sort of stuff. So you actually want to know about where your mushroom is growing and what environment before you yourself consume it. But overall, there's just a couple different main mechanisms, and when we come to the heavy metals, it is more of an absorption. Or when we're talking about I think the prelim for some of this, talking about how mushrooms or fungi might have the ability to take nuclear waste in water streams or nuclear waste, but all it can really do is bind the radioactive nucleotide to itself. It's not going to eat it or break it down, it's just taking it out of the environment. Or there's weird things like they've understood in Chernobyl is they've found mushrooms growing right in the nuclear reactor site, and where nothing should live. And it's the ability for mushroom to, the fungi itself, to self-repair its DNA faster than it's being broken apart by the radionucleotides. And so it's just the amazing ability of fungus to withstand all these different environments. Where it comes to polyaromatic hydrocarbons and these other ring structures, is they actually break those rings. They take those rings and they break them up and then and even degrade it a little farther. But once that process happens, then other bacteria or natural attenuated things, sunlight can break down oil pretty well once it's out of that ring structure, and water. And so it creates a more bioavailable like less toxic structure that other things can break down once the fungus are done. And so depending on what you're going after is what the end product it can be. But the metals aren't necessarily going anywhere, they're trapped within the fungus. And that's where I was talking about trying to create less of a mess, is to create a low heat ash incinerator. And so you end up carbonizing everything else, like the corn cobs, it's just a woody biomass, and then the fungus. And then you'd be left with a little bit of carbon and metals. And so less of a mess.
I think one thing to keep clear is that unlike the toxic organic compounds that are actually being digested and broken down, heavy metals aren't going to change chemically. They're always going to be there. And so our goal with heavy metals is not just to remove them from the water, but to try and sequester them and to put them someplace where they're not going to cause trouble. In remediation efforts that we're doing in Ecuador, they were using this basically to fertilize bamboo or to fertilize inga, large wood trees, and to thereby lock up the heavy metals in a wood product or some sort of building material that was going to be outside of, sequestered away from where it would have biological activity.
Basically what we're doing with the heavy metals is you've got a large volume of water with a fairly low concentration of metals in it. I mean, enough to be nasty for the fish and the bugs. But you're taking a very large volume of water with a relatively low concentration of metals and concentrating it down to something you can deal with. That, if you can deal with, you get 30 or 40 times 30 or 40% of the weight of the cells now become metals, you've cleaned up a lot of water and now have a very small amount of residue left to do something with. Maybe recover the metals. If you have to bury it, you can bury it somewhere else, or it's a very small amount of material compared to the amount you started with. And this is one of the issues with the Berkeley pit in Butte, is the volume in there is staggering. I don't remember how many billion gallons there are now in the pit, but it's filling at a rate of 5 million gallons a day, give or take, of heavy metals. And the solution to that currently is to just add a lot of limestone and raise the pH, make it very alkaline. The heavy metals will precipitate out, and now you have sludge, which is basically heavy metals in Drano, and now you've got to do something with it. And it's about 25% of the volume you started with is now this sludge, and that's just going to landfills. And if you had a biological system, we would reduce that down to where instead of 25% of the volume you started with, it would be a fraction of a percent of what you started with once you burned away the carbon. And that's the difference. You have a much, much smaller amount of material to deal with.
Thank you. That's very illustrative. I know that you spoke to this a little bit earlier, but I wanted to open up the question to everybody. What do you all see as being the cutting edge of mycoremediation? Obviously, we were just talking about how folks have been tinkering around in labs for decades at this point, being like, see, this filter works, I swear. But in terms of what's happening in our community or in Montana at large, what's the cutting edge?
I can start with paper that just came out in PNAS Scientific Journal last week, I believe, from the University of Illinois, where they did a study of agroforestry and mushroom harvest, and they found that this was a viable way to both sequester carbon and produce protein. In fact, it was a more efficient means of producing protein on a per hectare basis than raising livestock. So I'd urge you to check out that paper. It's in PNAS, the journal, and it's regarding the use of agroforestry and mushrooms to produce protein sources. Okay, so that's just one recent thing that just came up this last week. More about food production and carbon sequestration than actual remediation, but it does kind of tie in with what we're talking about. So, did you have something?
Well, we tried to talk about the cutting edge a little bit and just scale. We've got to scale these things and get them on the landscape. That, you know, when Mark is talking about fungi for his soil building, that needs to be scaled. And we've talked about, Egan mentioned, in trying to inoculate some of that slash so it degrade with a white rot fungus and produce an edible mushroom at the same time. So those are things of scale. And remediation from like petroleum waste, I mean, the only way to deal with these issues is we're going to have to put on-site fungus production capacity at the site of some of these major oil spills, and that's because the only way to clean them up. And that's to us is the implementation question, is the big issue of cutting-edge research. How do you get this out there at scale and finance it at scale? We built a fungus factory in Butte years ago that produces a fungus that kills bugs, kills insects. It's a myco-insecticide, and that has a capacity to produce 27 tons of fungus culture in a single batch in about 10 days. And that's small compared to what we need to be building to deal with this.
Thank you.
Yeah, I would just say the same thing. I mean, part of the shift has been societal, and academia and everything else has figured this out a while ago, but more and more society, mushrooms are starting to be so much more in pop culture, and people can realize how much they can do about medicine and your human biome to psychedelics and how it can improve your brain and fix your psyche or help restore PTSD and normal human function. So I think the world is moving that way to utilizing biology, and understanding biology can help fix some of our problems that we've created. And so anecdotally, I think this kind of shift where people are more aware of how much fungus can do, and mushrooms themselves. It was for so many years everybody just said mushrooms are toadstools and you got to avoid them and don't eat them because they're dangerous and all these things. So we're taking steps into now, like, hey, oyster mushrooms, they can break down toxic waste, but they also have every essential amino acid you need as a food, which so few organisms do. And so just understanding just the possibility of mushrooms in general, I think that's helped kind of shift. And so I think we're getting to where the technology could be somewhere good. But yeah, I mean, it's at scale, and we have ideas on how to get this to scale and build a fungus factory and make deliverable things. But it's hard to do it without anybody paying for the infrastructure.
Absolutely. So. I know that some of you have been speaking to various applications of mycoremediation, whether it's super specific or kind of at large, but I'm just curious if there's any other places in western Montana where you see there being just a ripe application for mycoremediation, whether that be a specific site, like you've mentioned the Berkeley Pit and that big dioxin site in Butte. Mark's been talking about roads or pseudo roads in National Forest. But is there any other locations or sites that you think would be really appropriate?
Pipeline spills.
Yeah, pipeline spills have been in the news a lot, the big ones in Kansas. I mean, some of the issues with pipeline spills and like the Keystone, it's dilbit. It's not your normal petroleum. It is the thickest, hardest sludge that they have to actually cut with other things to make it flow through the pipe. And so once that's spilled, I mean, you think oil floats on the surface of water and do whatever. This stuff sinks immediately and becomes this toxic sludge at the bottom of waterways and does all these other sort of things. It's the fractions of oil can be kind of the problem is what you deal with and the heavier stuff. Nature has a way to deal with a lot of the lighter things, and the sun burns them off and stuff. But it's all these different products that like the petroleum industry makes that it's going to be hard. And so the pipeline spills, and like Cliff was saying, we just submitted a grant from the Department of Transportation, actually went out and solicited bioremediation. Like, the Department of Transportation doesn't think about this a lot. But they actually asked people to write grants to do bioremediation of oil spills or other hazardous material. And that was a pipeline hazardous and transportation division of DOT. So we can hope that we get the grant and get a chance to work on some of that. And then close to home, I mean, North Dakota, all the oil fields there, I mean, it impacts, we've done agricultural research over there, and there's a lot of people that have defunct wellheads on their site that is just toxic forever. But if we could clean up each little wellhead site, it could go back to agriculture. I mean, this is in Yellowstone, floodplain, beautiful ag land that is now there's just oil wellheads everywhere and pump jacks and tanks holding the oil, and a lot of them are just sitting there defunct without anything to do with it. So, I mean, we can clean up and restore the landscape and work with people that way. I mean, there's a lot of easy instances on how this could be applied on the landscape.
The site that's closest to Missoula is Stone Container. I mean, Stone Container has pits full of dioxin held back out of the river by dirt bank berms, no lining, nothing. There's tens of thousands of cubic yards of hydrocarbon contaminated soil. They're still surveying, trying to figure out how much waste there is and where it all is. But we need to be part of that process and get biology into that system. It turns out that one of the amazing places, one of the highest concentrations of spills at Stone Container was the lifts they used to dump the chips out of the trucks and spilled hundreds and thousands of gallons of hydraulic fluid in big puddles around where they lifted. And nobody knows what to do with that except dig it up and haul it to Utah. And so they're working on the site. It's a long-term project, but we need to get involved and get biology considered by the regulators in dealing with this site right out here.
Cool. Thank you. And absolutely agree. Every time I'm foraging down by the river there, I'm always just a little bit like, I don't know if I want to go any further. Well, so you've spoken about how a lot of the barriers to entry around this are either cultural or financial. Who, hypothetically, if mines were of a different mode, who would be funding these projects? Mycoremediation projects.
Superfund.
The perpetrators,
Yes,
Superfund.
And in other parts of the world, in Ecuador, local people brought lawsuits against, actually the first class action lawsuit ever in Ecuador was suing Chevron to clean up the mess, and they won, and to the tune of $9 billion to clean up the mess in Amazonia and Ecuador. Chevron's response to that was to close down operations and just leave. Shell in Nigeria, Royal Dutch Shell, has just lost a lawsuit last year brought by plaintiffs whose water supply and fishery was totaled, and they've won. And but last I read that Shell is appealing that decision. So one of the things we need to do is make the companies that made the mess responsible for cleaning it up.
Cheers to that.
Accountability is definitely a key factor in this. I think one of the other things that is motivating this again is the water fight. The fight for clean water, and I think that aligning the mycofiltration with water protector philosophy is a really strong common interest. We all drink water, right? Let's see a show of hands. How many people drink water? Yeah, okay. So, Yeah, should we open it up to questions, or do you have some more?
I have one more, and I think
Okay.
you have an answer for it, Larry. It is, how can amateur fungal enthusiasts get involved in this process?
Okay. Well, the fast and dirty answer on that is we have a contest for the next year where you can get cultures, fungal cultures from our cult group here with the WMMA, and you can grow your own mushroom experiment. People have done things, you'll see examples over there from mushroom paper. And Pedro, would you hold up the hat? We got that mushroom felt. You can go and feel that. That makes a nice hat there. We have paper products that we've made out of mushrooms. You see a couple bricks there of mushrooms where you can see how the reishi mushroom can be used for a construction product. And then Sydney's brought in a whole spool of brightly colored yarns there that are decorated with mushroom dyes. All of those have been, all those colors come from mushrooms that we have done during the various workshops. So we've got a few things here to try and inspire you to get some ideas. But again, you know, in memory of Robbie Flynn, we are offering a $500 prize for people who want to submit a new fungal idea. We'll try and have a show and a little demonstration next year around this time and share the results of this. So we'd like to invite you to participate in that.
And just to be clear too, this is a myco products and mycoremediation challenge. So there are prizes for first through third place. The idea is to encourage citizen science engagement in the vein of non-food product mushroom applications. So whether that is mushroom furniture, mushroom leather, or whether that's more like a myco filter or working on cleaning up soil in a certain part of town that you're aware of and have connections with. We're really excited about getting this word out to people who teach and young people in our community, because as I hope everyone understands, you know, we're not trying to incentivize with the amount of money that we do have, but knowing that someone who's a little bit younger, that this is just a very promising exercise for them, especially to be involved and to know that they can contribute a really meaningful idea to our community and what we're trying to do here. So now we're going to open it up to everybody else. I'm going to come around and you say what you got to say. Hi.
I've got two questions, and I think, Cliff, these are for you. One is the problem of deep aquifer pollution, and I wonder if mycoremediation can do anything about that. And the other one is something you touched on, and that was like high latitudes. And so we're doing a lot of bad things in the Arctic in terms of exploring and getting at oil. And with those high latitude problems comes pollution, and you mentioned that it's not so effective in the cold climates. So if you can address those, I'd appreciate it.
Yeah, deep contamination that's really deep, either in an aquifer or in soils that are, you know, in contact with an aquifer. Most of the organism white rot fungi that are going to deal with dioxins. That's one of the issues in Butte, is that some of that's really deep. The organisms that, you know, white rot fungus need oxygen, so you're going to have to dig it up and treat it, and then put it. Once it's clean, you can put it back in the hole, or some of the water can be pumped, treated, and pumped back. But those are issues when they're really deep like that. But there are also issues for conventional remediation. I mean, digging holes that deep is going to cost a lot of money no matter how you deal with it. And the issue of cold weather is, I mean, that's probably why we should not be drilling oil wells above the Arctic Circle. It's just, you know, it's, like I said, you can actually go to the beaches where Exxon Valdez crashed and turn over rocks and find crude oil just sitting there on the beach, 20 years, 30 years later. And that's an issue. 40 years, that's a lot. Yeah, I'm showing my age here. Yeah, when you make a mess, that's going to be one of the issues with the tar sands. Summer's pretty short in McMurray, and there may be ways to keep them warm. I mean, people have looked at, I've read theoretical studies of using solar kind of collectors for warm air, and you can build above ground biopiles where you aerate them with tubes or something, and can keep them warm with warm air. But that's going to be expensive, but probably not as expensive as destroying the Arctic National Wildlife Refuge.
First of all, thank you all very much for an incredible presentation. The video is actually pretty exciting watching particle board breakdown. Great soundtrack too. My question for you is, can you elaborate a little bit more on the language of the EPA regulations that are thwarting your efforts to bring this to current sites?
Oh, man. We don't have enough time.
Oh, God. Yeah. There's RCRA, TSCA, and Superfund, and collectively those would be a pile of documents about 4 feet tall on the desk here. There's a process of becoming a generally recognized, what's the right word here?
Approved contractor?
Yeah, you got to be a approved contractor. You've got to have a past proven technology, and there's a whole bunch of rules for how that has to happen in demonstrations, and it's
kind of like trying to get a new drug certified by the FDA, right? I mean, it's a process. How's that? Yeah.
One of the things we've talked about and tried to do, and are still talking to some established remediation companies that work with the remediating sites all the time now, and dealing with the regulations on a daily basis, and trying to team with them to have some demonstration projects. And we've been talking to a company in Butte that does this, and sort of try to ease our way into that. And we don't have any desire to be a full-service remediation company. I don't want to know all the rules and have to dig up all the dirt and operate bulldozers, but we could sell fungus to companies that do that. And so there may be ways into this that we're working on, but I can't begin to explain the ins and outs of the regulations in the time we have to take the rest of the week. I mean, there's a whole document. EPA has just, to codify part of this proposal we wrote to the Department of Transportation, we looked into the latest landfill rules on landfills, and just the rules on landfills were 40 pages. And that's just how you take care of your landfill, not how you deal with it. It's just crazy.
One more thing with that, we got lucky in doing that Elkhorn project. I have a relationship with the Big Hole Watershed Committee, and they have been contracted to help restore and work on this site in the Elkhorn Creek. And so we're getting in the door when it's trying to be planned and funding and to get everything working. So we actually got a grant through the Beaverhead County DNRC. So to work with that, and so it's building these collaborations to get the information out there, to know what's possible, and to work with people, and to start off from the ground and the grassroots, and to actually get access to toxic waste sites or acid mine drainage sites or something. It's not something that it's easy to get your hands on. Most people don't have their personal toxic waste site that we can come in and clean up, but yeah. So that's why ideally we want to work, like Cliff was talking about, there's this engineering firm in Butte, but they've been in preliminary talks with some people out in eastern Montana to clean up small, old, defunct oil well heads, and to just start off these things and to be able to prove technology on a small scale. And so then you can start breaking in through the bureaucracy and say, look, we can do it. We've demonstrated it. Let's keep on putting this into the regards. Keep this in the process. Let's design the system so it works all the way into cleaning up these things. So.
So I know we're talking about mycoremediation, but I had a question about the application of mycelia in the actual physical practice of restoration. And I don't know if this can be answered, but my basic understanding of the benefits of mycelia, one of which is prevents soil erosion. Could mycelia then be utilized to then either reinforce or harden stream banks or river banks to prevent erosion, especially when it comes to stream restoration or river restoration, and thus not having to utilize things like coconut husks and then reduce carbon footprint of the manufacturing of things and things like that?
I'm not sure it would be strong enough for a stream bank. Usually we use things like root wads and, like you said, coir fabric and things like that, but mostly they're natural materials kind of woven together, big logs and such. The fungal mats that you're talking about are a heck of a resource in the forest environment. You know, that chunk of wood, that chunk of soil I was holding up in the photo here, that was held together by mycelium. And so in the forest environment, it's extremely important, and I'm not sure that would transfer to a stream bank.
Yeah, I just wanted to riff a little bit because we're with the Big Hole Watershed Committee and we're helped kind of get that project. We're kind of in the business of putting ourselves in the middle of the bureaucracy and pounding our heads against the wall for a long time to try to eke the money out. It is possible. In our case, it really started with Ben, who was approached. It was an issue. We knew it was a fisheries issue, so we came at the project site trying to figure out the contamination to the fishery. And it takes a while. You got to characterizing the site and doing everything that you do to sort of understand the scope of the problem. God, I don't know. It's kind of a non-answer to say, but it based on the relationships that we built with the project managers at the Forest Service, and we built enough trust with them, I guess, that we could put together a project. We brought money in just to do basic soils characterization, and then it was, I don't remember how we did it, but in the course of a conversation of planning, I was like, hey, there's these crazy guys that do this stuff with mycelium, and we could do it, and why don't we do a pilot? It took 2 years for us to get to the point where they were like, yeah, that sounds good. But there was only one grant source in Montana that we could find that would even fund a pilot study. So Clean Water Act money won't fund it because it's not a past proven technology. So we had to go to a mine site, the state's DNRC reclamation planning grant program. And there's only so much you can do with $50,000. But we're going back to them now, and we've got these guys now money to sit at the design table with engineers, so that when the engineers are doing what they do, and people are going to go with the path of least resistance. So right now, the path of least resistance is big machinery, dig it up, put it in a pit, cover it with dirt. That's like literally all we know how to do. So to do more than that, you've got to have somebody willing to sort of carry that ball and ask more of other people to sort of think outside the box, and persistence, I guess. That's a pathway, right? So if you're looking for, oil well, wellheads and abandoned places, there are giant tomes of bureaucratic language. Don't ever read them. Just find the person that manages that and push until they tell you to stop. And when they tell you to stop, you find the next person that, you just got to keep pushing. But it takes forever, and you'll lose all your hair.
I have a clarification question. When is the past? Like, when you're saying it has to be a past-proven technology, when is the past? When did it have to be, proven by for it to be relevant? And then I have another question after that, but...
20th century. No, again, the process of becoming a proven technology is it's a bureaucratic nightmare, and it doesn't have anything to do with the science. I don't know how to expand on that.
My question is probably mainly for Mark, but in case anybody else doesn't know, that the Lolo National Forest land management is being revised right now, and so that's going to influence how like all of the forest around us is managed for a good long while. Public engagement is on right now, and it's going to kind of continue and to ebb and flow. There's going to be a lot of different information. So if it could be like, if all the people in this room or watching the recording later could help in any way, like what would be your dream scenario? What could we do in the public comment period of the National Forest Land Revision?
On the forest plan, that stuff's already in there. Woody debris standards have been in there for 20 years. Now, forest plan stuff and what happens on the ground are two very, very different things, and they don't jive at all. So I don't care what they throw in the forest plan. It doesn't matter to me. Jeff, you could answer that. The disjunct between forest plan and the real world. None. That was your answer right there. Yeah. Yeah, those things are already in there, and they're in there pretty solid. They have great recommendations, and all their pretty words are nice. But that's lovely words. But that's about it.
Anybody else have any? Oh, okay.
This might be kind of a basic question, but I come from more of the wildlife world. When I think about biocontrol and that kind of thing, you talk about, treating things, right where the issue is happening. And I, flash back to like cane toads in Australia, things like that. Is there any risk of, that type of, invasive species when you're moving different species of fungi to different places like that?
Of course, yeah. I think one of the most obvious examples is the yellow oyster that has been introduced, Citropinellus, that has been introduced as a commercial edible and then allowed to escape into the wild in the eastern part of the country. And this is an Asian species that is completely taken over a lot of hardwood habitats. It's great. It's nice that it's an edible. Another example of invasive species of mushroom is something that Paul Kruger's been studying up around Vancouver in the Pacific Northwest, is the introduction of the Amanita phalloides, the death angel or the destroying angel, being introduced on the roots of trees from Europe. And this happened back in the 1800s, 1900s, when these trees were introduced. And these fungi have taken off and grown in the soil. Besides the fruiting bodies being toxic, we really don't know what the effect of these fungi in the soil is. Another one that we might look at is the sudden oak death syndrome that has been in California. And, this is another one that is believed to have been introduced through horticultural stuff. All these have been introduced intentionally, right? We haven't got really accidental mushroom transfer, because in that mushrooms can throw spores everywhere around the world. They can already go there. But you kind of need, what would you say, a certain environmental preconditions for establishing a population in a new area like that. So yes, I think I would say that, considering how much back and forth there is with mushrooms, that it's a pretty minor problem compared to the invasive species problem we see with a lot of plants. But I'll hand that over to you guys and see other opinions too.
When we're doing remediation work, we work only with fungi that are naturally occurring in the habitat where we're working. We don't, so we're working with, in bioremediation, we're working with oyster mushrooms that are local isolates or ones that are common. Rhizopus for remediation of heavy metals. Rhizopus is everywhere. You can walk out in your backyard and pick up a handful of soil and it'll have rhizopus in it. So we're very careful about that. I mean, it's something we pay attention to. And bless their hearts, the Department of Transportation actually asked that question in their proposal solicitation.
I'm sorry, Jeff. Someone that hasn't talked is over here. I think this will, if everyone doesn't mind, I think these will be our last two.
This question is for Mark. Is there an optimum size of carbon to leave on the forest floor?
Yes. 6 inches plus. Yeah, the small stuff decomposes a little too quickly, and it doesn't have great contact. Also, the bigger stuff, you were talking about red or brown rot and white rot. We actually like the brown rotters that leave that brown cubicle rot in the forest, and only the large trees can leave that behind. So yeah, the bigger the better. And
Coarse woody debris.
yeah, it's a big deal. And right now we're having huge fights with the circus about leaving debris. The fire guys have got everybody down, and we're leaving less than 2 to 3 tons per acre on way out of prescription, way out of forest plan standards.
Yeah, the fuels rhetoric that's driving a lot of the forest management discussion now, I think, is really damaging. This whole idea that everything is a fuel and treating all wood as fuels is really projects the wrong idea for a lot of people because wood is not only the one of the main sources of fuel, it's the only source of water retention. So, I mean, yes, it's bad when you've got fuels on the soil, but it's really bad when the sponge is burning. You know, I mean, when the sponge is burning, that's what we're looking at right now. We should have a lot more sponge and a lot less burning on that. So, Jeff, yeah.
Answer for Mark, popped into my mind after I missed the opportunity. But the forest plan revision process right now is in the assessment phase, and that's a technical term for them gathering scientific issues. And I think later this week there's a public meeting. It may be online. It may be, I know it's at least online. And people can just tune in and even get involved with part of the discussion. This is where anybody can suggest scientific topics. And so that later on, if you talk about the science of remediating compacted road surfaces, later on, during the phase when they're talking about actual forest plan standards, then we could talk about requiring those kind of steps that you do. And those things don't actually exist as in detail as we like. And yeah, all these other kinds of scientific issues that you've been talking about, Larry, you're just mentioning. This is the time for people to get involved and push the science. And the forest plan revision process is required to listen to people. And sometimes it takes pushing. It always takes pushing. But this is the time. So look on the forest plan revision website for the Lolo National Forest. It'll tell you when these meetings happen. Thanks.
Thank you very much, Jeff. That's really helpful. We should post that on our website. I'm going to close out questions because we're 5 after and just want to respect everybody's time. If you are a member and you came here via the Western Montana Mycological Association's Instagram, website, Facebook, bless you. We're glad you're here. If you came here through the library, we're out doing other things in the community too. We encourage you to get on our newsletter, to become a member. We do a lot of events in our community. We have another one coming up here that's free and open to the public on May 2nd. It's going to be a mushroom identification session, which is always wildly popular. I would get here early because it's always a lot of people. And we're also having a tincture workshop, medicinal mushroom tincture workshop that's only open to members on April 5th. Every Memorial Day weekend, we have our annual spring foray, which is where we take people out into the woods and find, hopefully, last year was a real bummer, but hopefully lots of morels and make lots of good friends and keep the old ones. So if any of that's exciting to you, you can find us on Instagram, Facebook. We have a website that we're slowly updating. And yeah, Patreon is where we take our memberships and where we announce all of our limited release events that we're doing. So the QR codes are all over there. All the information about the challenge that was announced by Larry a few minutes back is also over there and can be found on the website as well. So if anyone has any questions about that, please feel free to reach out to talk with any of us that are going to be hanging out over there. We appreciate all of your time. Thank you so much for caring about this stuff.